Have you ever just stopped and wondered what's really going on inside your head when you feel happy or learn a new skill or make a tough decision? For like most of human history, the living brain was a total black box. You couldn't just pop it open to see how it worked. But what if we could? What if we could peek inside that box safely while it's running? Well, that's exactly what we're going to talk about today.
So this is the big problem, right? The brain is, without a doubt, the most complex thing we know of in the universe, and it's sealed up tight inside our skulls. So how in the world do you study it? How do you go from just guessing about what it's doing to actually watching it in real time without any harm? That's the incredible question that the field of neuroimaging finally started to answer. For the longest time, our only real shot at studying the human brain was, well, after someone had died. And yeah, that gave us a basic anatomical map, but it told us absolutely nothing about the living mind. You just can't dissect a thought or a memory or a feeling from cold tissue. And that's the crucial point. It really boils down to this. We need two totally different kinds of information. First, yeah, we need the map, the physical layout of all the structures, its anatomy. But a map by itself isn't enough, is it? We also need to see the traffic on the roads. We need to see the brain's activity, which areas are firing up, which networks are talking to each other. That's the information we were missing.
Okay, so this brings us to this incredible field of neuroimaging. It's basically a whole suite of technologies that finally let us peer inside the living brain and see not just the map, but the traffic too. So let's break down exactly what that means. So at its heart, neuroimaging is all about creating pictures of our nervous system. But it's not like it's just one camera. You should think of it more like a whole toolkit, with different tools designed to look at every single aspect of the brain, from its physical shape all the way down to its chemical pathways. This really is the best way to think about it. The two main approaches. On one hand, you've got structural imaging. That gives us the brain's blueprint. It's like a super detailed architectural drawing showing all the parts and how they're connected. Then you have functional imaging. That's the live video feed from inside the building. It shows us which rooms have the lights on, what's happening right now. The action. All right, let's start with that blueprint. How do we create a super detailed, three-dimensional map of the brain's physical structure without ever picking up a scalpel? Well, the star player here is a piece of tech you've probably heard of, the MRI. Now, we're not going to get into the deep physics here, but basically, an MRI is a giant, really powerful magnet. It makes the water molecules in your body, and remember, your brain is mostly water, all line up in the same direction. Then, the machine zaps them with a radio wave that knocks them out of alignment. As they snap back into place, they give off this tiny little signal. By listening to all those signals, the MRI can build the stunningly precise 3D map of your brain. And this is where it gets really clever. By just tweaking the machine settings, kind of like changing a filter on your phone's camera, doctors can make different types of tissue pop. A T1 scan is fantastic for seeing the overall anatomy. See how the fatty tissue is bright, but the fluid is dark? But with a T2 scan, both fat and water show up bright. Now look how that fluid is all lit up. This makes it perfect for spotting things like swelling or disease. But of course, no tech is perfect. The upside of MRI is massive. You get these ridiculously detailed 3D images, it's totally non-invasive, and there's no radiation involved. The downside? Well, the machines cost a fortune, they are incredibly loud, and if you're claustrophobic, it's a real challenge. Plus, you can't go in one if you have certain metal implants like a pacemaker. Okay, so we've got our blueprint. We have the map. Now for the really cool part. Let's switch on the live feed. How do we actually watch the brain think? For that, we turn to a different flavor of MRI, one of the most powerful tools in all of modern neuroscience, functional MRI, or as you'll hear it, fMRI. And this is the key distinction. An fMRI machine is basically the same hardware as a regular MRI, but it's not looking at the structure of the tissues. Nope. Instead, it's looking for the telltale sign of brain activity, and that sign is a change in blood flow. Why blood flow? Well, because your brain is incredibly greedy. Just think about this number for a second. Every single minute, your brain demands about 750 milliliters of blood. That's a huge amount. It doesn't store any fuel, so the second a part of your brain gets busy, it immediately screams for more oxygen and your blood vessels deliver. So here's how it all works. It's called the BOLD effect. That stands for blood oxygen level dependent. When a bunch of your neurons fire up,
Boom, oxygen-rich blood floods that area. And here's the genius part. Oxygen-rich blood has different magnetic properties than oxygen-poor blood. The fMRI machine is so sensitive it can actually detect that tiny magnetic change. And that's the signal that tells scientists, hey, right here, this part of the brain is active right now. Okay, this is all fascinating science for sure, but what can we actually do with this information? I mean, how does this help people in the real world? Well, let's look at a powerful example of how these scans are starting to change how we treat one of the most common mental health conditions out there. You know, the tough reality for so many people with major depression is that finding the right treatment is just this frustrating game of trial and error. Less than half of patients actually get better with their very first treatment, whether that's medication or therapy, so it's often a coin toss. Wouldn't it be amazing if we could predict which treatment was going to work best for a specific person right from the start? So to try and solve this puzzle, researchers turned to another type of functional scan. This one's called a PET scan. With a PET scan, you get an injection of a tiny, tiny amount of a radioactive tracer. Just think of it like a smart dye that latches onto a specific molecule, like glucose, brain fuel. The scan then tracks where that dye goes, which shows which parts of the brain are burning the most energy. So in this really groundbreaking study, scientists did PET scans on patients with depression before they started any treatment at all. Then, these patients were randomly assigned to get either an antidepressant or a course of cognitive behavioral therapy. The big question was, could anything in those initial brain scans have predicted who would get better with which treatment?
And what they found was just astonishing. It all came down to the activity level in one specific part of the brain, the insula. It was incredible. Patients who had low activity in their insula responded really well to therapy, but not to the medication. But for the patients who had high activity in that exact same spot, it was the complete opposite. They responded well to the antidepressant, but poorly to therapy. This was the first time a brain scan could actually point to the right treatment path. It's a huge leap towards personalized medicine for mental health.
And a study like this just opens up a whole world of possibilities. We're slowly moving away from this one-size-fits-all approach to mental health and toward a future where a simple brain scan could help guide the most effective personal treatment plan from day one. So really, the question isn't if this technology will change how we treat the mind, but how profoundly and how soon.